Solving the Kepler problem using only Newton's laws, high school level math, and an intuitive approach to the concept of limits. Video 1. Introduction and Review of Relevant Math. Before we go ahead, let me say a brief word about the concept of limits. If you're not familiar with the concept of limits in mathematics, you're going to get familiar very soon. There are two approaches to the concept of limits, a formal approach and an intuitive approach. The formal theory of limits comprises a set of precise mathematically formulated definitions and theorems. It is the very foundation of calculus. A less precise, more intuitive approach will be sufficient for our purposes, although I will give you a glimpse of the more formal approach as we go along. Approximations and intuitions are perhaps underappreciated as to their importance in the progress of science. We now recognize that Newton's theory of gravity is itself an approximation to Einstein's general relativity. Nevertheless, it is a very, very good approximation, except in relatively extreme circumstances. When Johannes Kepler joined the great Danish astronomer Tycho Brahe in Prague, he gained access to voluminous observational data obtained by Tycho documenting the motion of the planets over decades. The data, far more comprehensive and accurate than anything else available at the time, forced Kepler to draw the momentous conclusion that the planetary orbits were not circular, contrary to the sacrosanct beliefs of the ancient Greeks and of the great Copernicus himself. He eventually found that the orbit of Mars was elliptical, and he inferred that all planets must have elliptical orbits. He formulated two other empirical laws. Here are his three laws. Number 1, the orbit of a planet is an ellipse with the sun at one of the two foci. Number 2, a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. Number 3, the square of a planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit. As a means of introducing some key concepts, let's talk about Kepler's second law a bit. Planets sweep out equal areas in equal times. The area swept out depends on two variables, the speed of the planet, v, and the distance from the sun, r. For any given r, the area swept out per unit time increases as v increases. Conversely, for any given v, the area swept out increases as r increases. Therefore, Kepler realized that in order for his law to be true, the speed of a planet must be lower when it is farther away from the sun by just the right amount, as this diagram illustrates. We can state the law in terms of symbolic algebra as A is proportional to T. A helpful way of thinking about proportions is to recognize that the two quantities are variables, but that one always varies in proportion to the other. Another way of stating this relationship is to say that the ratio of one variable to another is a constant. So we can write A divided by T equals K. Remember K for Kepler, or K for Kepler's second law. K is a constant for a particular orbit. Now we can let T vary from 0 to any positive value. For our purposes, when dealing with such varying quantities, it is helpful to modify the notation just a bit. So in this case we write delta A divided by delta T equals K. The delta symbol represents a finite change, and we can read this equation as stating that for any change in T greater than 0, the ratio of the change in A to the change in T is a constant. We can also write this equation as delta A equals K times delta T. Delta A and delta T are finite quantities, meaning that they are always associated with real numbers. As we move forward, there will be times when we want to think of delta T as decreasing more and more, until it becomes infinitesimally small, and we want to have a special notation for such a small quantity. Now, as delta t becomes infinitesimally small, delta A does so as well, by a proportional amount. So let me show you how we will express such quantities using this relationship here as an example. We will say dA divided by dt equals k, or dA equals k times dt. Newton would refer to such quantities as infinitesimals or vanishing quantities. As an aside, the first step in inventing calculus is to develop an intuition and a methodology for dealing with infinitesimal quantities and their ratios. Newton came up with his own notation for infinitesimals when he invented the calculus. Leibniz, who invented calculus as well around the same time, developed a different notation. We are borrowing Leibniz's notation here, which happens to be the conventional notation in calculus today. Newton was particularly concerned with the ratio of two vanishing quantities. In this case, we can say that because the ratio of delta A to delta T always equals K, according to Kepler's second law, we know that the ratio of dA to dt is always equal to K, without needing any further proof. However, in other cases, the ratio of two quantities might not be constant. Let's take two hypothetical variables, delta x and delta y. Let's assume that they are a function of a third variable, for example, delta t. Let's say the ratio of delta y to delta x is only approximately equal to some other quantity, or ratio of quantities. Call it z. Now it may be that as delta t approaches 0, and both delta y and delta x get closer and closer to 0, the approximation becomes more and more accurate, until eventually it is correct to say dy to dx equals z. That is, the ratio of infinitesimal amounts of y and x equals some finite value. However, in accordance with modern standards, you can't write this equation unless you have a rigorous proof that it is true, in accordance with the definitions and theorems of the formal theory of limits. According to the conventional jargon, one would say, in the limit as delta y and delta x approach 0, the ratio of delta y to delta x equals z. Then one would have to prove that dy divided by dx equals z using a formal methodology for constructing such proofs. For now, let me mention the notation that I will use. When the ratio of two quantities clearly gets closer and closer to a certain finite value as the two quantities get smaller and smaller, I will put an arrow from the ratio to the finite value to indicate that our intuition tells us that the approximation is good enough for our purposes, and instead of concerning ourselves with whether an actual equality can be proven or not, we will simply assume that a true equality exists as we make additional calculations based on these ratios. The Principia was Newton's magnum opus in which he formally presented his three laws of motion and his universal law of gravitation. These laws served as the theoretical foundation for just about everything else found in the Principia, including not only his derivation of Kepler's three empirical laws, but also his explication of a variety of other phenomena, such as, for example, the variation in the magnitude of the tides from one day to another, and the precession of the Earth's axis over a cycle of 26,000 years. Newton did not create these laws out of thin air. They represent in part a synthesis of the ideas and discoveries of some of the other contributors to the scientific revolution, including, perhaps first and foremost, Galileo. I reviewed in detail how Newton synthesized these ideas and then further developed and organized them in another video you can find on the Voltaire's Garden channel. It is the final video in the series entitled From the Ancient Greeks to Isaac Newton, early astronomers, and the birth of science. I will review Newton's laws briefly here. Here they are. The law of inertia postulates that a body at rest will remain at rest unless an external force acts upon it, and that a body in motion will maintain the same velocity in terms of both speed and direction unless an external force acts upon it. The second law states that if an external force does act upon a body, it will cause an acceleration or a change in the body's velocity. In other words, force equals mass times acceleration. Another way to think of this is to write it as follows. A, acceleration, is proportional to the force and inversely proportional to the body's mass. The third law states that for every force there is an equal and opposite reciprocal force. Now, in the case of the interaction between the Sun and a planet, the mass of the planet is so relatively small that we will ignore its reciprocal effect on the Sun. Instead, we will assume that the Sun remains stationary, even though the combined effects of the planets do in fact cause the Sun to wobble a bit. Newton's universal law of gravitation states that the force of gravity acting between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. G is the gravitational constant of proportionality introduced by Newton to make the equation consistent with the units employed for all three variables. Of course, new theories must be tested, and the perfect test was already immediately available to Newton. He could test whether his theoretical laws explained Kepler's empirical laws. In fact, Newton's laws did provide an appropriate framework for solving the Kepler problem, but it would not be a simple task. When Newton succeeded in solving the Kepler problem using only his three fundamental laws of motion and his universal law of gravitation as a starting point, it was the culmination of the scientific revolution. So, what if a mere mortal wanted to understand how such a feat might be accomplished? One option would be to go right to the source and read Newton's Principia. But be prepared for some tough sledding. Even though Newton invented calculus, and calculus is now the conventional approach to solving the Kepler problem, Newton relied instead on complex geometric constructions and demonstrations to prove his points. Understanding his arguments required advanced knowledge of geometry, including some obscure principles going all the way back to the ancient Greeks. As a Cambridge student at the time allegedly commented as Newton walked by, "There goes the man that writ a book that neither he nor anybody else understands." Following Newton, advances in physics and mathematics allowed the solution to become purely formulaic. These advances included an understanding of the conservation of energy and the principle of least action in the context of Lagrangian and Hamiltonian mechanics, coupled with advanced techniques in solving differential equations. So another option would be to learn some advanced physics and calculus and see how to solve the problem using differential equations. Then you could go on YouTube and find a video like this one showing you how to work through the problem line by line by line by line. For the typical armchair scientist, mastery of these tools might take quite a long time. Moreover, the abstract nature of these tools is far removed from our own visualization of the phenomenon of planetary motion. No doubt Newton would have found his purely geometric approach more intuitive, more elegant, and more visually satisfying. A third option would be to read this book, Feynman's Lost Lecture. In 1964, Feynman was invited to give a guest lecture to the freshman physics class at Caltech. He chose solving the Kepler problem as his topic, something that he had been working on for his own amusement. He proposed to solve the problem without explicit reference to calculus, using almost exclusively geometric arguments, just as Newton had done. This is how he began the lecture. I am going to give you what I call an elementary demonstration. But elementary does not mean easy to understand. Elementary means that very little is required to know ahead of time in order to understand it, except to have an infinite amount of intelligence. He first demonstrates Newton's proof of Kepler's second law. Then he says to the class, with regard to proving the law of ellipses, I always have trouble following Newton's logic, so I decided to cook up an explanation of my own. Once again, however, his geometric arguments, such as those illustrated here, might be difficult to follow for someone who had not studied any geometry after the 10th grade. One issue that comes up is that with a purely geometric approach, one never arrives at an equation for an ellipse. It would look something like this. In order to solve the Kepler problem and arrive at an equation, you need the tools of analytic geometry, a field founded by Descartes just 50 years before Newton's Principia. And to apply the tools of analytic geometry, you first of all need a coordinate system. A polar coordinate system with the sun at the origin would be a good choice. The two coordinates that identify the location of a planet are r, the distance from the sun, and theta, the angular position of the planet relative to the chosen reference direction. With these tools at hand, you can ask the following quantitative questions. For any given set of initial conditions, namely the location and velocity of a planet, what is the overall size, shape, and orientation of the elliptical orbit? How do the initial conditions account for the eccentricity of the ellipse? And for any given angular position of the planet, relative to a reference direction, how far is the planet from the sun? Now let's add a hypothetical orbital path to the diagram of our coordinate system. At one point, Kepler thought orbits might have an ovoid shape. I'm going to use the ovoid to remind us that at this point we are not assuming the orbit is an ellipse. In addition to r and theta, there are two more relevant quantities that we want to identify now. First is the instantaneous velocity vector of the planet. The velocity vector is always tangent to the orbital path. A moment's reflection should convince you that it would be logically inconsistent for it to be otherwise. Second is the angle phi shown here, formed by r and the velocity vector. Another moment's reflection should convince you that the following three statements are true. If phi is greater than 90 degrees, r is increasing. If phi is less than 90 degrees, r is decreasing. And if phi is equal to 90 degrees, r is not changing. So let's begin our attempt to solve the Kepler problem using high school level math. We start with a review to jog your memory. How would we know if these two triangles are congruent? If each pair of corresponding sides have the same length, they are congruent by the side-side-side rule. If two pairs of corresponding sides and their intervening angles are equal, the triangles are congruent by the side-angle-side rule. Finally, if any two pairs of corresponding angles and one pair of corresponding sides are equal, the triangles are congruent. If two triangles are congruent, naturally their areas are equal. We need to remember the general rule for finding the area of a triangle. The area is 1/2 of the base times the altitude. Once a base is chosen, the altitude is a line segment drawn at right angles to the base, connecting the base to the opposing vertex. Any side can be chosen as the base, but sometimes the altitude is a little less obvious. In a case such as this, the base can be extended far enough so that a line segment can be drawn perpendicular to it to the opposing vertex. Here again, the area is 1/2 of the base times the altitude as drawn here. We need to recall that opposite angles of intersecting lines are equal. Also, alternate interior angles are equal when a third line intersects with two parallel lines. The distance between two parallel lines is always equal whenever it is measured by a line segment that is perpendicular to both. Trigonometry allows us to relate Cartesian coordinates to polar coordinates. So, for example, y divided by r equals the sine of theta. Therefore, y equals r sine theta. Similarly, x divided by r equals cosine theta, or x equals r times cosine theta. Now consider this diagram. S here is the arc length of a segment of a circle. In accordance with basic principles of geometry, S equals r times theta. Just remember that for relationships such as this to be true, theta must be expressed in radians. To indicate that neither S nor theta is fixed, and that both can vary over a wide range, I am going to express this equality differently, consistent with our previous discussion of varying quantities. So delta S equals r times delta theta, or alternatively, the ratio of delta S to delta theta equals r. Here I have drawn a chord, D, whose endpoints correspond to the endpoints of S. So now we have formed a triangle whose sides consists of the two radii plus the chord D. Here I have drawn an altitude of this triangle. I have labeled it delta A because it too will vary as theta varies, as follows. Delta A equals r times the sine of delta theta. Now let's ask what happens to sine delta theta as delta A and delta theta approach 0. It's clear that as delta theta approaches 0, delta A approaches 0. And if delta A goes to 0, then the sine of delta theta must go to 0. But what about the ratio of theta to sine theta? Let's switch over to infinitesimal notation and I'll show you the answer. The ratio of sine d theta to d theta goes to 1, or the sine of d theta goes to d theta. This is an actual trigonometric limit formula. There is a very clever proof based on geometry and trigonometry. If you're interested, I have reproduced the proof at the end of this video. For now, let me just show you a graph of theta and sine theta to help you visualize their relationship near zero. As you can see, as one gets closer and closer to zero on the x-axis, the graph of y equals theta and y equals sine theta converge. This is not a formal proof, but it is compelling visual evidence that perhaps sine theta and theta truly are equal in the limit, as they both approach zero. The issue of the ratio of vanishing quantities had for a long time been the subject of debate, sometimes of fierce debate. Here is how Newton tried to explain his position.
Newton wrote, "It may be objected that there is no such thing as an ultimate proportion of vanishing quantities, inasmuch as before vanishing the proportion is not ultimate, and after vanishing it does not exist at all. But the answer is easy. The ultimate ratio of vanishing quantities is to be understood not as the ratio of quantities before they vanish or after they have vanished, but the ratio with which they vanish."
With all that said, let's go ahead and make a substitution for sine theta above. So, dA equals r d theta. Well, ds and dA both equal r d theta in this setting. So we conclude that ds equals dA. Now look at the diagram on the left. Does it bother you that ds, d theta, and dA do not look like infinitesimal quantities? It doesn't need to bother you. If the quantities were drawn to scale, we couldn't visualize what's going on. Consider what James Gleick in his biography of Newton said about Newton's diagrams. He drew lines and triangles that looked finite, but were meant to be on the point of vanishing. Now consider the area of the sector of this circle shaded in purple. Call it dA sub s. From geometry, we know that dA sub s equals 1/2 times r squared times d theta, which I now want to rewrite as 1/2 times r d theta, so that now we can substitute ds for r d theta. Now consider once again the triangle formed by D and the two radii, and its area dA sub t. The area of a triangle equals 1/2 times base times height, or in this case, 1/2 times r times dA. Now, since ds equals dA, we conclude that dA sub s equals dA sub t. One can use a similar approach to finding the area of the sector of any smooth closed curve. Take our ovoid, for example. Choose an appropriate point for the origin of a polar coordinate system. Now choose a sector and assume you have an equation for this ovoid, expressing r as a function of theta. We can estimate the area of the sector by constructing a triangle. We can draw in the altitude and then compute its area. The area equals 1/2 times r sub 1 times r sub 2 sine theta. We could divide the sector up with additional radii to create n triangles, each having a central angle equal to the original central angle divided by n. The approximation becomes better and better as n increases. If we let n go to infinity, then by definition, the area of this sector of the closed curve is the sum of the areas of all the triangles. It might seem backward to define the area this way, and it might seem weird to think of summing an infinite number of quantities. But that's exactly what you do in integral calculus. And in many cases where there is an alternative way of calculating the area, as in the case of a circle, for example, one finds that the two methods agree. As you will see in the next video, the actual calculation of the area is not necessary for our purposes, and so we don't need to know anything more about integral calculus. I just wanted you to understand how one can use the concept of limits to define the area bounded in part by a curve.
You are now prepared to proceed to video 2, proving Kepler's second law. But first, if you would like to see a proof that the ratio of sine theta to theta equals 1 as theta goes to 0, you may watch the remainder of this video. So here's the proof that sine d theta divided by d theta equals 1. I have drawn a triangle and its altitude within a circle centered at O. The radius of the circle is 1. Let me clarify my notation with some examples. OB with a line above refers to the line segment OB. OB bracketed by a pair of forward slashes refers to the length of line segment OB. Arc AB bracketed by a pair of forward slashes refers to the length of arc AB. However, when I refer to these terms as they appear on a slide, for the sake of brevity, I will simply say OB, for example, instead of the length of line segment OB. By definition, arc AB equals theta in radians. The two radii in this diagram, OB and OA, both have a length of 1. BC is less than AB is less than arc AB, which equals theta. This statement, and many of the statements that follow, are obvious enough by inspection that I won't provide a more detailed geometric proof. But just know that such detailed geometric proofs do exist. BC equals OB times sine theta, which equals sine theta. So, sine theta is less than theta. And sine theta divided by theta is less than 1. This last statement is something we'll need later, so let's draw an orange box around it. Let the tangent lines at A and B intersect at E. Arc AB is less than AE plus BE. And BE is less than DE. So, theta, which equals arc AB, is less than AD. Also, AD equals OB times tangent theta, which equals simply tangent theta, which equals sine theta divided by cosine theta. Therefore, theta is less than sine theta divided by cosine theta. And cosine theta is less than sine theta divided by theta, which is less than 1 from our earlier finding above. Now, in the limit as theta goes to 0, cosine theta equals 1. And it cannot be that at that limit, 1 is less than sine theta divided by theta, which in turn is less than 1. So we see that the ratio of sine theta to theta gets squeezed by the other two terms in this inequality as theta goes to 0. In fact, there is something called the squeeze theorem,
which allows us to state that in the limit as theta goes to 0, sine theta over theta equals 1.